So today we're going to apply a real-life example of calculating or sizing our base plate and anchor rod for this column that's loaded in compression and has a bending moment. Before we get into it, I'm just going to kind of give you an overlay of how this was set up and how this was organized. We have our input data here, so we have design variables like the length and width dimensions of our base plate, our plate thickness. We also have beam column width, which is going to be the width of this beam column that's loaded from this end to here, and then the number of bolts on a row per side, so that's actually going to be anchor rods. Number of anchor rods per side, that's a design variable. You can change that. We have bolt edge distance, which is the distance from the outer edge of the base plate to the center of the anchor rod. And then we have our allowables. We're going to need these to calculate our margins of safety. And then here's our loads that are acting on this column. And then we have a factor of safety. We will incorporate into our margin calculations. And then we have a graph you can generate here, which we'll cover in another video. But you can see here we have our inputs and then we have our calculations with our outputs. So that's how this is organized. We have three sections: our concrete bearing strength, our base plate strength, and our anchor rod strength, and we calculate margins for each of these. So that's what we're going to go through. I'm going to walk you through how to set this up while applying some Excel VBA functions to help simplify our calculation procedure. So let's go ahead and get into it. So the scenario we're looking at is going to be a column loaded with a point load of 800 pounds and then a moment of 40,000 pound-inches. So the first thing, if you recall from the slides, we wanted to size our base plate large enough so that it wouldn't fracture the concrete. So if we look at our figure over here, what we want to do is we want to take into account the footprint area that the base plate is pushing on, and then we want to also calculate the worst case stress and compare that to our concrete bearing allowable. So if you look at these two loads, they put a compressive stress and a bending stress, with our worst case being on the outside edge when you sum these together. So we're going to calculate this value right here. What's the value of that stress at the edge of the base plate that's pressing on the concrete? So to do that, we need to calculate our bending moment of inertia for our the area that it's pressing against on the concrete. So I wrote a VBA function. It's called rectangle moment of inertia. So in this case, it's going to take the width, which is going to be our base plate width, and then it's going to take our height, which we consider, if we flip this 90 degrees down and then move this moment over, you'll see that in the distance from here to here is going to be our y. So it's going to be our height. So that's our bending moment of inertia for that. Next, we want to calculate our worst case stress due to the compressive stress. So that's simply just going to be force over area. So the point load divided by the area, which is going to be the area of our base plate. So it's 8 psi. Now we need to calculate the bending stress on the outside edge. So we're going to use this equation right here. And we wrote a VBA function for that. Bending moment stress. It's going to take our bending moment acting on that area, which is 40,000 pound-inches. Our y is actually going to be n divided by 2, because our neutral axis is going to be down the middle of this column right here. So we have 0 stress in the middle, and we have our worst case stress at n divided by 2. And it's going to give me a negative here, but because I've drawn this and I know I got to add these together, I'm just going to go ahead and just make this positive. So if I sum those, I get my max stress on the outside edge. It's 248 psi. So now we need to calculate a margin of safety taking into account our factor of safety and our concrete allowable. So the function for that is margin of safety, and it's going to take our allowable, in this case it's 4,000 psi, in our input section our factor of safety of 3, and then our load is going to be 248. And so you can see our margin of safety is positive, which is great. As long as it's greater than 0, our design is sufficient. The next thing we want to do is we want to look at our cantilever analogy. So we're looking at the yield strength of the base plate on this outer edge right here. We're going to treat it like a cantilever. So the stress that we're putting on the concrete here, well, it's going to be equal and opposite on our base plate. And so I've shown that here, and you can actually what we're going to need the length of our cantilever. So that's going to be this equation right here, the length of our base plate, which is n minus the width of our column here. So the width of our column is going to be 3, and then we're going to divide by 2. So it's 3.5 inches. I'm going to go ahead and just change this to 4, make it an even number, 3 inches. And if you recall, if we treat our cantilever beam as 1 inch wide beam, so you can see here, down here, we treat it, the cross section as 1 inch wide, we can actually make a simplifying assumption, and it ensures that we can convert our stresses that we calculated up here to line loads. That greatly simplifies the analysis. You can go derive that. It's pretty easy to do, but you can either derive it or believe me. But what we're going to do is we're going to have to calculate our line load or our stress at these values. For a uniform load, it's simply going to be equal to the stress we calculated up here, our uniform compressive load. The next thing we want to do is we want to calculate our line load at the beginning of at the base plate right here, and then the line load, this long one, at the end. Then we can break it down into 2 areas and then calculate the areas of those to get equivalent forces. So I'm going to calculate this line load right here first. So that occurs at the width of our column divided by 2. So if we look at this, this may help you visualize this. We're calculating the bending stress right here at this value, at this point right here. If we go down from this to down here, it's going to be this value. So the VBA function we're going to use is bending moment stress, but we got to realize it's actually a line load in this case. I'm going to make that negative because I know what direction it's pointing in. So our bending moment is going to be 40,000 pound-inches. Our Y is going to be the width of our column divided by 2, and then our moment of inertia is going to be 833.33. And so that's our line load at this spot. Now we need to calculate the line load at this spot. So that corresponds to the outer edge right here of this bending stress. So use the same VBA function, bending moment stress. So our moment's going to be 40,000 pound-inches. Our Y is going to be N divided by 2. And our I is going to be this value. And so we get 240 pound-inches. So we have our line loads now. Now what we want to do, if we go over here, we want to convert those to equivalent forces so that we can calculate our worst case reaction loads at the base plate, because this is going to be where our worst case bending moment is, and also our worst case shear. So to do that, I wrote a VBA function, and what we're doing is we're just calculating the area under the curve, and then we're finding the location at which that equivalent force happens. So for this uniform load right here, the VBA function is equivalent uniform load, And we'll go into this code. It's going to take the length over which the uniform load acts, which is going to be the length of the cantilever beam, 3 inches. And then our line load is going to be 8 pound-inches. And it's going to return our equivalent force and where it acts. In this case, it's going to act halfway down the beam, so at 1/2 times the length of the beam, which is going to be 1/2 times 3, 1.5, so boom. The next thing we want to do is calculate the area of this uniform load, so A3 right here. So we're going to use the same function, equivalent uniform load. The length of the load is 3 inches and the line load is going to be 96 pound-inches. So that's our force and that's where it acts. And so now we have to calculate the area of this triangular section, so 1/2 base times height. So the function is going to be equivalent triangular load. The length over which it acts is 3 inches, and then the line load value is actually going to be the difference between this point line load right here and this line load at the beginning, because we just want this area. We already took into account this uniform area. So that's simply going to be 240 minus 96, and it acts at 2 inches from the base. So now that we have all our equivalent forces and their locations as shown here, we just apply the equations of equilibrium, or the equilibrium equations, to determine our reactions. So if we look at this free body diagram, the reaction at A is simply going to be the sum of these forces. So I sum these, and then our moment, they have it's this equation right here. It's just going to take the forces and multiply it by their distance from the base and then add them together. So Excel has a function called sum product, which does this calculation for us. I didn't make this. It takes an array and it takes another array, and what it does is it multiplies the force by the corresponding value in the other array and adds them together. So that's our reaction moment. So now that we have these, we can do our failure analysis of our beam. So if you remember, we got to consider two things when we have a beam in bending. So on the top and bottom, you're just going to have tension and compression, and then in the middle, you're going to have a shear just acting on it. So we have to look at both those situations. So the first thing we want to do is calculate our bending moment of inertia of this beam. So it's going to be bending, it's going to be the function we used earlier, rectangular moment of inertia. In this case, our width is going to be 1 inch as shown here, and our height is going to be our thickness. So width is 1, I'm just going to put that in, and then our height is up here in our input data, our thickness. So that's our bending moment of inertia of this beam. So the next thing we want to do is calculate our bending stress on this bottom element. You can see here that our bottom element, due to these forces, is going to be in tension. So we simply use bending moment stress equation function, VBA function, which is defined by these equations. I wrote the equations out to the side in case you didn't know, but there they are. And it's going to take our moment, so it's going to take our reaction moment at the base, and then our y is going to be our thickness divided by 2. And then our I is going to be the bending moment of inertia of our beam that we just calculated. And I'm going to make that positive. So that's the tension stress acting on this bottom element. So now we're going to analyze this middle element. You only have shear forces acting on it, or shear stresses acting on it. So I wrote a VBA function for that, rectangle max shear. It's simply just going to take our area, so our cross sections, our dimensions, so it's going to take 1 inch, and then our thickness, which is 2 inches, and then our worst case shear, which in this case is going to be our reaction at A. So we have calculated our stress values for those two situations, the bottom of the stress element and the stress element at the middle of the beam. Now we have to calculate margins of safety for both. So we're going to use, when you're looking at just a stress element under tension, von Mises stress, basically your allowable from von Mises stress is going to be your yield stress. So margin of safety, so our allowable in this case is going to be our yield stress of the base metal. In this case, it's 36,000. Our factor of safety is going to be 3, and then our load is going to be the value we just calculated on that element. So that's our margin of safety. It's positive, which is great. Now we need to look at our shear. So because this element's only in shear, you can use a correlation to determine our shear allowable. It's simply going to be 0.577 times the yield stress. So if we go up here, I wrote a function. It's called shear yield. It does just that. It takes our yield stress and multiplies it by 0.577. So if we do that to the side, bang. So we have these two values equal each other. So we know that function's right. So our margin of safety for this is going to take our shear allowable, which is this value, our factor of safety, and then our load. Click the wrong value there. Our load is going to be right here. And so our margin of safety is positive. So that's great. So we've concluded our cantilever beam analysis of our base plate. Next, we need to look at this free body diagram right here. So what we're doing here is we're going to determine the force acting on our anchor rods. And there's more than multiple ways to skin this cat, but what I did is I assumed the point load was acting at the end here. That simulates the tipping condition, which is the worst case you can come up with. And then I'm going to calculate my force on these anchor rods using this free body diagram. But once again, I just want to emphasize there's multiple ways to do this. This is one way I'm doing it. It makes sense to me. So what we've done here, all we're doing is we're using our moment equilibrium equation. We're summing the moments about the reaction at A here. If we do that, we end up with this equation right here, and you can derive that. That's what it comes out to be. So it's going to be our moment acting on this column minus the axial load here acting on our column. So it's going to be 800 times n divided by 2 divided by, it's going to be n minus our edge distance. And so that's the force load acting on along the line of our anchor rods. The next thing you want to do is pick a number of anchor rods to put on this side, and then you can determine how the forces are acting on it. So the more anchor rods you add, it distributes the force. It cuts down the tensile load on each anchor rod. So in this case, it's going to be our total force divided by the number of anchor rods, and that'll be the force acting on one anchor bolt. So up here, number of bolts per side is a design variable. I chose 3. So that's the force acting on our anchor rod. The next step we want to do is calculate a margin of safety. So if we go up here, we can actually go select. They have a table. This comes from the American Civil Engineers book. I can't remember which one, but I'll post it in the description. But so basically the force acting on the anchor rod with 3 bolts per side is going to be 1,500 pounds. And so if we look at our allowables right here, our 5/8" OD diameter anchor rod has a allowable of 10,000 10 kips, which is 10,000 pounds. So 10,000 exceeds 1,500. So I'm going to go ahead and just choose that one right there. So I put my allowable in here. I put it as 10,000. We're going to go ahead and calculate our margin of safety. So our margin of safety is going to be our allowable 10,000, our factor of safety, and then our load. So 1,400 pounds. I guess I said 1,500, but that's our margin of safety. So bang, we set up our spreadsheet. Now we can go toy with this and see how things react. So if you look at this, our concrete bearing strength is 4.38. You know, that means we have over designed this thing, so we can change our base plate area and see what we get. So let's change it to 5 by 5. Our margin of safety should change, and it does. It's negative, so we need to make our base plate bigger than that. So let's make it 6 by 6. And so our margin of safety is positive in that case. And then we have, for our base plate, our design variable is our thickness. And you can see our margins of safety here are telling us that our base plate thickness is sufficient, but it's too big. We've over designed this thing. So let's change our base plate thickness to 0.5. Okay, now we become negative, so that's too small. So if we change this to 1 or 0.75, what do we get? So check it out. Our design right here is better now because we've decreased the size and we're spending less money on the base plate. So you can toy with that. And then our anchor rod strength, you know, it changes based on the number of bolts and also on the other variables, but in particular it's positive right now. You know, I may want to just see how this changes with the number of bolts. So let's say we do 2 bolts, anchor rods per side. I keep saying bolts, but I mean anchor rods, and it's negative, so we got to add more anchor rods. So 3 was sufficient, but you can toy around with that. And then down here we've calculated our bending moment diagrams, which I'm going to go to in a later video. I use some Excel VBA to do that, but there it is. There's our shear and bending moment diagrams, derived from our singularity functions, and there's another term for it. But anyways, we've covered a lot here, and I've went through it step by step. I hope you understand what was done. I hope I made it easy. But now that we've gone through the spreadsheet, let's go take a look at the code. So this is the code that was written to do an analysis, and so essentially it's just the equations off here to the left. That's all it is. I know there's a couple things in here that may be difficult to wrap your mind around, but this is our rectangle moment of inertia. It's this equation. Our bending moment stress is my over I. And then our equivalent uniform load, this essentially just takes the area underneath our curve. So if we look at this again, the area of the uniform load is going to be length times, you know, the line load right here. That's simply just what I did here, length times width, and I return also the point at which it acts. So it's going to be L divided by 2, and so I stored it in 2 variables, and then I returned it in this form. Then this triangular load, 1/2 base times height. Simple enough. It acts at 2/3 from the base, and then it returns it. And then our margin of safety. This is very versatile. I use this everywhere. It's just one function. I can use it for stresses, forces, all sorts of things. So I call it allowable, and you know, it's just this equation right here. And then shear yield, here it is, 0.577 times our yield stress. And so that's really all there was to it, guys. That's a pretty simple function to write. I'll post this, and you guys have fun doing this. This is a great exercise for a mechanical engineer to do. Not only does it help you figure out how to organize things, but it also gets you exposed to some coding, and also gives you a refresher on free body diagrams and loads, and all that stuff, how to simplify problems. Because keep it simple. That's my best advice to you. If you make something complicated, people don't understand it, they're just not going to believe you. You can be the smartest guy in the world, but if you can't convince others to believe you, well, you're at a loss. So that was just my 2 cents, and I hope you liked the video, and I'll see you next time. Adios.